All right. Hello, welcome back, class. We're going to continue our discussion on phase transitions. And specifically, we're going to flesh out an object that we've been discussing a little bit indirectly, which is that of a phase diagram. Now, phase diagrams contain an enormous amount of information. They summarize regions of parameter space, parameters that we can control, things like the temperature or the pressure or the density, and over which ranges of those parameters we find specific phases, or where we find phases in coexistence with each other. They demark lines of which abrupt behavior occurs, like a vapor spontaneously changing into a liquid, condensing, or a solid spontaneously melting into a liquid. So they contain a lot of information, and yet with the tools of thermodynamics, we can say some pretty general things about what sorts of phase transitions are possible, and therefore what phase diagrams look like. So let's remind ourselves of a simple example, that of boiling or condensation. And let's see how phase diagrams projected into two different axes, say the temperature and density or temperature and pressure axes, relate information about that same liquid vapor transition. Okay, so let's start over on the left with the temperature density plane. If I was going to think about where a liquid state was likely to be, well, a liquid state is something that occurs at high density as opposed to low density. I might imagine there's a liquid phase over on this side of the phase diagram. Over on the other side of the phase diagram at low density might be a vapor. Indeed, what we mean as the distinct difference between these two states of matter is, in fact, their density. A liquid is necessarily higher in density than its vapor. Now, there are regions, if I put those two liquids and vapors in contact with each other, that vapor would have a specific density, as would that liquid. Now, if I put liquids and vapors into coexistence with each other, for example, forming a solution at the bottom, or liquid at the bottom, a vapor at the top of some beaker, the liquid wants to have a specific density, the vapor wants to have another density. As I move along this line, all I'm doing is I'm changing the amount of that liquid with a fixed density relative to the amount of vapor. At every point along this line, for those two states to be in coexistence with each other, it necessarily is the case that their temperatures are the same. To be a state of equilibrium, the vapor has to have the same temperature as the liquid. Otherwise, heat would flow. This would not be in equilibrium. And indeed, this is a line of constant temperature. Let's go ahead and label that temperature T0. Now I could do the same construction at a lower temperature. There would be a different density of the vapor and different density of the liquid, that if I put them into coexistence, they would keep. I could do this also at a higher temperature. And if I draw a line for the locus of those points, that would form a so-called coexistence curve. It's just the locus of points for where, if I put liquids and vapors into contact, what is the density of the liquid and what is the corresponding density of the vapor. Now, each one of these lines could be constructed from an experiment by which I actually took a vapor and compressed or cooled it down at fixed pressure. As I cooled it down at fixed pressure, I would see the vapor spontaneously condense. So let's draw that path in another color. So I cool the system down at a fixed pressure. I would see it condense, generating some amount of liquid until I got over here, in which case if I continued to cool that liquid down, I would have removed all the vapor, having only liquid left, and then the density of the liquid would just start to change, increase. This line, therefore, is an example of an isobar, a line of fixed pressure. Okay. One easy way to remember the shape of these liquid vapor coexistence curves and the temperature and density plane is that they kind of look like spooky ghosts out of Pac-Man. Okay, so that's what one of these phase diagrams looks like in the temperature density plane. What does this corresponding phase diagram look like in pressure and temperature plane? Well, we know that things are going to be, in some sense, fundamentally different. Temperature and pressure are special types of thermodynamic variables in a way that density is not. Temperature and pressure are potentials for spontaneous flow. Temperature, the potential for spontaneous heat flow. Pressure, the potential for spontaneous volume flow. Density, on the other hand, is not a potential. It's a mechanical variable. It just takes the ratio of the number of particles to the volume. And because pressure and temperature are potentials for flow, we know that a state at equilibrium has to have equal pressures across it and equal temperatures across it. Otherwise, that volume or heat will flow. So this line, this coexistence line in red, the dashed red, must collapse onto a point because every position along this line, this one here, is a state at which liquid and vapor are in coexistence. And for them to be in coexistence, they must have the same pressure, even though they need not have the same density. Okay, so let's try to use that intuition to fill in this phase diagram. Well, first, where in the pressure temperature plane am I likely to see a liquid? So that's at higher pressure and lower temperature. Correspondingly, I'm likely to see a vapor at higher temperature. Now, if I was to do this same experiment where I, at fixed pressure P naught, go from the vapor to the liquid, we denoted T naught as being the point of coexistence. In this diagram, that line, which existed on the temperature density plane, now collapses onto a single point of coexistence, which is one of a number of points that trace out a coexistence line. A coexistence line because it's only on this locus of points that I can have a vapor in coexistence with the liquid. It must be that the pressure and the temperature of that liquid are equal to the pressure and the temperature of the vapor it is in contact with. In fact, we know, just for completeness, let's go and sketch in examples of liquids and vapors. Okay, we know actually how to define this line. There's a precise mathematical definition for determining that line. And that is, not only do the temperatures and pressures of the liquid and vapor have to be equal, but their chemical potentials do as well. So if I was to know the functional dependence of the chemical potential on temperature and pressure, that line must be a line in which the chemical potential of the liquid is equal to that of the vapor. Now there are two arguments for those functions, temperature and pressure. And so I have one equation, two unknowns. There's not a unique solution. In fact, there's a line of solutions in the temperature pressure plane, and that line is exactly what we've just found. Okay, so let's start employing thermodynamics to try to understand what we can say in general about the shape of those coexistence curves. This will rehash a calculation we did on Monday. So let's start with asking this question. What can we say about the shape of coexistence curves in the temperature and pressure plane? Now there's some expectation that there will be some simplicity associated with that question, precisely because temperature and pressure play such specific thermodynamic roles. So let's try to ask this in general. Let's consider a phase alpha in contact with a phase gamma. And we'll do this in the pressure and temperature plane. Okay, let's imagine that phase alpha lives up there, phase gamma lives down here, and there is a coexistence curve that looks like this. Every point along this curve, say at T naught and P naught, we know something about. We know that each one of those points what is true? Well, if that lies on that coexistence curve, it must be the case that the chemical potential of phase alpha is equal to the chemical potential of phase gamma. Now imagine I took that system and I heated it up a little bit by some amount dt. If all I did was heat it up, well, I'd go from a region of coexistence where alpha and gamma could be held in contact to a case in which gamma would be preferred. But imagine at the same time of increasing the temperature, I increase the pressure. By some amount dP. Now, if at T naught plus dt and P naught plus dP, at that new point, phases alpha and gamma still coexist, I made a change in temperature and a corresponding change in pressure in a specific way, such that I fall back on that coexistence curve. What must we know about the change in the chemical potentials? it must be the case that the chemical potential for alpha and that for gamma, they must still be the same. And not only that, if they're the same at those two different points, then their changes must have also been the same. So if we move along this coexistence curve, not only do we know that the chemical potentials are the same, but if I make manipulations to the control parameters, pressure and temperature, and I stay along that line, then it must be that the chemical potentials of alpha and gamma, in order to stay equal to each other, change in the same way. So if we're going to think about how chemical potentials change as I manipulate temperature and pressure, there's a natural equation to do that with. That, of course, is the Gibbs-Duhem equation. Again, Gibbs, you all remember, Duhem lost to history. Maybe one day we'll find out what happened to him. The Gibbs-Duhem equation relates the temperature to changes in the pressure and changes in the chemical potential. And what goes with temperature is entropy. What is conjugate to pressure is volume. And for the chemical potential, the number of particles. If I rearrange this equation and divide by n, I could solve for the chemical potential by bringing it over to the right. That will leave me with the entropy, if I divide through by n, divided by n, times changes in temperature, minus the volume divided by n, times changes in pressure. At coexistence, or more specifically, along coexistence line, we just deduced that the changes in the chemical potential of alpha must be equal to the changes of the chemical potential for gamma. And now we have explicit expressions for how those changes are imposed by changes in temperature and pressure from the Gibbs-Duhem equation. So substituting that in, on the left, we'll have the entropy per particle for phase alpha times changes in temperature, minus the volume per particle for phase alpha, changes in pressure. These are not raised to, these are of alpha. That must be equal to the entropy per particle for phase gamma times changes in temperature, minus the volume per particle for phase gamma times changes in pressure. If we define this little thing, the entropy per particle, as a little s, and the volume per particle as a little v, and we have them for each phase. And let delta S equal the entropy per particle for phase alpha, entropy per particle for phase gamma, and delta V be the corresponding changes in volume per particle. Then we can rearrange this equation, solving for temperature, and we find that along the coexistence curve, the change in the pressure as a function of the temperature is equal to delta S over delta V, or the change in the entropy per particle for alpha, change in the entropy per particle for gamma, over the change in the volume for alpha minus the change in the volume per particle for gamma. So indeed, generic for any system, any phase transition, I didn't even tell you what phases alpha and gamma really refer to. We know the shape of a coexistence curve. If there's a coexistence curve, we can predict its slope in the pressure and temperature plane by knowing how the entropy changes across that phase transition and how the volume changes. This equation, for all its use, it has a fancy name. It's called the Clausius-Clapeyron equation. Very useful in the construction of phase diagrams. So let's see how this actually works in practice. Let's think about some examples. Let's go back to boiling. So for boiling, what is delta S? Is it positive or is it negative? If I go from liquid to vapor, the corresponding change in the entropy is positive. There are more microstates associated with the vapor than that associated with the liquid. And what about the change in the volume? Of course, it is positive. That's what we mean by boiling. That's the fundamental differentiation for a liquid relative to a vapor, is that the vapor has a larger volume per particle. This means that dP dt along a coexistence curve for a boiling transition, well, both delta S and delta V have the same sign. They're both positive. So it means that dP dt must be positive. So that must have a positive slope in the pressure and temperature plane. Now, how steep that slope is depends on the relative size of the change in the volume and the change of the entropy, and they're both large. So we should expect that dP dt is kind of small. The ratio of two large numbers is not a large number. Okay, let's think about a different transition, melting. So that takes a crystal into a liquid. So delta S for this transition, the liquid less than the crystal, was that positive or negative? How many more microstates do you think a liquid has relative to a solid? Almost always this is positive. And nearly always it's large. Okay, what about the corresponding change in the volume? Oops. How do we expect the volume of the liquid relative to the crystal to be? Do we expect the volume of the liquid to be larger than the volume of the crystal, or vice versa? Oh, we don't really know, right? If I was to cool carbon dioxide and freeze it, the volume of its crystal would be smaller than its liquid. But we know counterexamples. We know if we cool water, the volume of its solid is larger than the volume of its liquid. So we don't really know the sign. And also there are two condensed phases going from the solid to the liquid. There isn't a large volume change. So the change in the volume is small and could be positive or negative. So while dp dt along coexistence has a sign we don't know, if we looked at its magnitude, I'm taking a ratio of a large number, a large change in entropy, to a small number, a very small change in volume, we know that its magnitude is large. Right? So now actually we could write out what a typical vapor, liquid, solid phase diagram must look like as reasoned through just from basic thermodynamics. So in the pressure, temperature plane, let's work through this. So where are we likely to find the vapor? Well, it's at high temperature. Where are we likely to find the crystal? Well, it's at low temperature. And the liquid then is somewhere in between. Okay, so the liquid vapor transition, we said, has a positive slope. But it's not all that sharp, it's not that large. The liquid crystal transition, well, it might have a positive or negative slope, but on this linear scale, that slope is so large, it's going to look just like a straight line. Okay. So there's another transition we haven't explicitly constructed. A vapor can go directly to a crystal. Now, what do you think is the shape of that line? If you had to work it out through the same sort of principles we just used, the solid vapor transition line, is it going to have a positive slope or a negative slope? Do the entropies and volumes change in the same way? So a vapor relative to a crystal certainly has a larger volume. What about the entropy? Is the entropy of a vapor larger than the entropy of a crystal? Of course it is. So it will also have a positive slope. Is there a bigger change in the volume of a vapor to a crystal compared to a vapor to a liquid? No, those are pretty similar. Is there a bigger change in the crystal entropy as it evaporates into a vapor? Yeah, there's a slightly bigger entropy. dp dt is proportional to that change in entropy, so this slope should be a little higher. and positive relative to the vapor, the liquid vapor transition line. Okay, so those are our lines. Now you all know that at some point, if I take a vapor and try to condense it into a liquid, there are temperatures and pressures over which I can stop doing that, which is to say that this line, the liquid vapor line, ends at a point. And we call that point a critical point. The existence of that point tells us something very deep about the distinction between a liquid and a vapor, which is that at some fundamental level, while they're distinguished by the densities, they aren't fundamentally all that different. I can imagine paths that take a vapor and continuously change it into a liquid. I can continuously change the density of a vapor in such a way, manipulating pressures and temperatures, that it smoothly transitions into a liquid. There is nothing structurally so distinct from a liquid and a vapor that prohibits me from doing that. And for that reason, there are points in the phase diagram where those distinctions between liquids and vapors actually cease. That's a critical point. Can I do the same sort of thing for a liquid as it turns into a crystal? Can you construct a path by which I take a liquid and continuously transition it to a crystal? What's the difference between a liquid and a crystal? Well, as we discussed last lecture, the fundamental difference is symmetry. A crystal has very specific planes over which atoms are periodically arranged. A liquid has both translational and rotational symmetry. Is there a way to continuously construct that periodic arrangement? No, by construction, that periodic arrangement is a very special state that happens only when all of those atoms are exactly in that position or close to it. And for that reason, there are no continuous paths that will take a liquid into a crystal. Because there are no continuous paths that can do that, this line has to continue forever. Now, it can have a bottom limit. It could continue to go all the way down to the zero pressure line, or could stop because something else happens. Now, you all have seen enough phase diagrams, presumably, to know that indeed typical phase diagrams, that crystal liquid line stops at a point at which those three lines meet. That point is known as the triple point. Now, we should be able to use thermodynamics to understand if that point is actually possible for three phases to coexist. What must be true? Well, if I looked at the chemical potential of the vapor at some temperature and pressure, it would have to be equal to the chemical potential of the liquid at some temperature and pressure. And those would also have to be equal to, at that point, the point of coexistence between all three phases, to the chemical potential of the crystal. Now I have two unique equations, the vapor chemical potential equaling the liquid chemical potential, and the liquid chemical potential equaling the crystal chemical potential. And I have two unknowns. namely, what are the temperatures and pressures which would allow for that equality. So indeed, two equations, two unknowns, that is a perfectly balanced equation. There's a unique solution, which means that there is a single point in the temperature pressure plane where three phases can coexist. And that point is then that triple point. A question then one could ask is, could four phases coexist? If I added another chemical potential, so I have the chemical potential phase 1, chemical potential phase 2, chemical potential phase 3, and the chemical potential phase 4, it must be the case that all four of those would be equal. If I only have two parameters and therefore three equations, there's no way to tune the temperatures and pressures in such a way to satisfy all of those constraints. At least for a single component system. What might happen if I had multiple components? Do I get a chemical potential that can depend on another control parameter? Yeah, if I have multiple components, the chemical potential should depend on the mole fractions of those components, therefore having more flexibility to satisfy those equations. So we'll revisit that in a second. Even though four phases can't coexist for a single component, that doesn't necessarily mean that single component phase diagrams are not complicated. For example, let's imagine water's phase diagram. And let's plot this in axes of temperature over on the y and pressure on the x. Now I'm going to consider very large changes in pressure, so I'm actually put the pressure on a log scale. Okay, so we're going to consider temperatures such that we don't even see the vapor. There's only a liquid here. And we know that at ambient conditions, there's a transition between that liquid and its crystal. And we know that ice floats. So by the Clausius-Clapeyron equation, we know that this line will have a negative slope. Now, that dp dt is very, very sharp on a linear scale. If I put it on a log scale, I can actually notice that it has a finite slope. Now, ice floats because the molecular arrangement of water molecules, as we saw in that video last lecture, is very open. There's lots of space between them. And in particular, the patterns that they form are little hexagonal rings. And for that reason, this ice is known as ice 1H, H for hexagonal. Now, what happens if I keep increasing the pressure? So that open arrangement of molecules takes up a lot of volume, has a low density. as I start pressing on it, there's a lot of room for the molecules to become much more compact. Water molecules in ice have coordination number 4. They form 4 hydrogen bonds. What's the coordination number for a system of just hard spheres? If I just put billiard balls together and try to pack them in the most efficient way, if I try to pack oranges into a crate, what kind of lattice would that adopt? Well, it wouldn't be so open as hexagonal ice. You would have about 12 neighbors. That 12 neighbors corresponds to something known as a FCC lattice. And indeed, if I take ice 1H and I increase the pressure enough, I will see a transition to another crystalline state known as ice 3, which is much more closed packed. Now, if I keep increasing the pressure, I will keep seeing other phases. Indeed, there is another transition to an ice known as ice 5. Turns out if I cool ice 3 down, there's a transition to ice 2. And while at no point can 4 phases coexist, there are many triple points in this phase diagram. It's interesting to note that people speculate that down here is another phase, the mythical ice 9, made popular by Kurt Vonnegut. Now, the kinds of pressures one needs to apply to see these sorts of behaviors are large. There's something like 10,000 atmospheres. Those are the sorts of pressures that condensed phases care about, because condensed phases are so incompressible. Now, I should note that ice 9 is not much more stable than all other ices. It doesn't have a lower chemical potential than ice 1H at ambient conditions. And so, unlike what Kurt Vonnegut said, if I threw a piece of ice 9 into the ocean wouldn't spontaneously transition into ice 9. Okay, so that's the complications that can arise in single components. Let's revisit now what can happen in a mixture. So a mixture is just multiple components, multiple molecular compounds. We have more parameters to vary. And therefore more possibilities for phase coexistence. There are still basic things we could say, basic constraints that thermodynamics applies. The basic condition in order to assert that we are at an equilibrium, that coexistence is maintained such that there are no flows in volume, heat, or number of particles. It must be the case that for each component, the chemical potentials are uniform across all phases. i.e. the chemical potential of component 1 in phase alpha, which will depend on temperature, pressure, and now the mole fraction of component 1 in phase alpha, and the mole fraction of component 2 in phase alpha must be equal to the chemical potential of phase gamma for component 1 with those same control parameters, its mole fractions, temperatures, and pressures. It's not that the chemical potential of compound 1 has to be equal to the chemical potential of compound 2, say in one phase, but rather that for each component, the chemical potentials have to be equivalent across all the phases. Now, those chemical potentials are complicated functions of the compositions, but they are what determines whether the mass will flow between the phases. So let's work out an example of such a mixture. Let's consider a boiling transition of two miscible fluids. This might, for example, be water and ethanol. It might be toluene or benzene, or a whole host of other two-component fluids. We'll specifically think about water and ethanol today. I think you will tackle a solution of toluene and benzene on your problem set. And let's do this at fixed pressure. Okay, so we're trying to work out the coexistence conditions for boiling. So let's imagine I have some liquid states. In contact with the vapor. Now that liquid might have some composition. Let's say if I have two components A and B, there's some amount of A and some amount of B. Now if that liquid is in coexistence with its vapor, it will have some composition. And that composition need not be the same. Indeed, if we were thinking concretely for the case of water and ethanol, which of those two species do you expect to be more enriched in the vapor? Probably ethanol. And why is that? Ethanol has a lower boiling temperature. It's more volatile at some specific condition. So generically, we would expect that the vapor phase to be enriched in that more volatile component. Let's assume that that's B for this example. Okay, let's consider then constructing the phase diagram. in the temperature mole fraction plane. So over here on the right, we have a solution that is only species A. Over here on the left, only species B. Now we're considering boiling. So at high temperature, we'll have a vapor. At low temperature, we'll have a liquid. Now, if I take a liquid at some fixed composition and I heat it up, there'll be a point at which I start to vaporize it. Now it has a fixed composition, some amount of A, some amount of B. If B is the more volatile, then I expect that the composition of the vapor has a smaller mole fraction of A. So that as I increase the temperature of some solution, when I reach the point at which it starts to boil, that composition can change. And in the case where we assume that B is more volatile, it will change such that the mole fraction of A is decreased. Now that sort of thing would happen if I started at one mole fraction or another. Say I start there, heat it up. I'm likely to get a vapor with a different chemical composition again. So I could do this experiment a bunch of times, tracing out then a coexistence curve, much as we have before. In the mole fraction temperature plane, I have liquid down here, vapor up there. When I have none of component A, it's pure component B. If B is more volatile, I expect that its boiling point is lower than if I have a pure solution of A. So if up here is the boiling point for species A, the less volatile component. Down here is the boiling temperature for species B. What we've just worked out is that the coexistence curve, the locus of points over which I have liquid vapor coexistence, forms an envelope by which, when I take a solution at some fixed composition, heat it to the point of boiling, I'm likely to see a different composition in the vapor. So that's the sort of complexity that can arise in mixtures and coexistence of mixtures and their phases. Like, this is an example which I think makes intuitive sense. I take a liquid that's less volatile. When I heat it up, I get a vapor which is depleted in that less volatile component. Could a vapor ever be enriched in a less volatile component? Let's think of a common example in the temperature mole fraction plane a mixture of water and ethanol. All right, at 1 atmosphere of pressure, we know that the boiling point of water is 100 degrees C. If you were to look it up, the boiling point of ethanol is 78.5 degrees C. If I do that set of experiments where I convert the liquid, a mixture of water and alcohol, to its vapor, indeed, I'd see something like this, a coexistence curve that enriches the vapor with ethanol until a point over which I start seeing the opposite behavior. This is not really to scale. This point occurs at a mole fraction of ethanol, which is equal to about 0.96. This curve is a very useful curve. Of course, this is how we actually distill alcohol, right? Essentially, we start with some mole fraction of alcohol in water, we heat it up, and if we collect the vapor, it's enriched in that alcohol. We can continue doing that until some point at which, if we were to heat the liquid up at this 96% ethanol, we'd get a vapor with that same composition. That point is known as an azeotrope, and the mixture therefore is an azeotropic mixture where the liquid and its vapor have the same composition. Indeed, this is the reason why you can't distill ethanol beyond 96%. I would not recommend drinking ethanol that has been prepared in higher concentrations from water, because such requires chemical agents, not just this kind of physical process of boiling. Okay, so that's all I have to say about the topic of these sorts of phase diagrams. We'll continue our discussion on phase transitions and phase behaviors next time.